Hey folks, how's it going? My name is Rosendo from MLH, as you probably know by now. Today we have a great guest joining us from MathWorks. His name is Connell D'Souza, and we'll be together exploring all of the amazing capabilities of MATLAB and Simulink. And honestly, I am just super thankful for everyone that's been joining us throughout the week, and today especially, just joining us to learn more about all of these amazing new platforms. Without any further ado, I just want to bring Connell on here so he can introduce himself.
Hello, everyone. My name's Connell D'Souza. I work on the education marketing team here at the MathWorks. So I help a lot of our customers at universities and students in general to use our tools to build cool stuff. So I'm not gonna waste too much time. I'm just going to jump right in. If you have any questions, please feel free to pop it in the chat. And if not, if you want to talk to us throughout the rest of the week, I know Rosendo set up a Discord channel for us, so we can talk through there. But without wasting too much time, I'm going to jump right. Oh, I'm hearing there's a little bit of an echo. Let me see if I can fix something here on my end. Okay, cool. So it looks like it. Yes, Celtics fans. We're not doing too well right now, but hopefully we'll get better. Anyway, so I'm not gonna waste too much time. Let's just jump in. I wanted to use this presentation to sort of give you an idea of what's possible with MATLAB. In terms of what we have as an agenda for today. We're going to talk a little bit about deep learning with MATLAB. I know deep learning is the new big thing. We've seen it come up a lot at a number of hackathons over the last couple of years. So, I just wanted to sort of show you what's possible with MATLAB, show you how easy it is to even without having a lot of experience with programming or having a lot of experience with deep learning, we can at least get you started. We're going to talk about some hackathon user stories, some cool examples of what hackathon participants at other MLH competitions or other MLH hackathons have built using MATLAB tools, and they've actually been pretty successful. So hopefully this is an inspiration to you as you embark on your journey with hackathons. And then finally, we're just going to point you out. I'm just going to point you out to some resources, some links that you can take a look at on your own time, snippets of code. Various communities that you can be a part of just to help you use our tools for the hackathon. All right, so the first thing I want to talk about is deep learning is a key technology that's driving this AI mega trend. So artificial intelligence, basically artificial intelligence. When you speak of it as a whole, it's the ability to enable machines to mimic human intelligence, right? And this has been some technology that's been around for a long time. Like you've had various scientists and engineers over the course of time trying to bring artificial intelligence to life. A few years ago, this concept of machine learning came out, where you had statistical models that enable machines to essentially learn tasks from data. So without you explicitly telling your computer, hey, perform tasks XYZ, the machine's able to or your computer is able to learn it based on certain statistical methods. And then the big change came around recently in the late 90s, early 2000s, with the advent of neural networks and deep learning. And essentially, what makes deep learning so powerful is that it's able to essentially learn things just based off data. So you don't have to do a whole lot to sanitize your data or prepare your data to have these deep learning models learn stuff from it. it's a whole other can of worms what they learn from that data, but at least these networks are able to, you're able to just feed it a lot of data and it's able to learn things out of it. Okay, so it's, deep learning is a part of our everyday lives. We've used things like speech recognition, whether it's through things like the Alexa or the Siri, or Google. You've got things like face detection. You've seen it in your iPhone, on your on your phone camera. It's able to identify your face or faces in pictures that you're clicking, as well as some more advanced applications like automated driving. You've got a lot of car companies now that are trying to add automated features to their vehicles, and that's definitely what the future is. Self-driving cars or driver assistance features. And deep learning is what's making all of this possible. So let's take a look at some applications of deep learning for images and videos. So what you see on the left is essentially a camera mounted on a car, and you see it's able to identify street signs. With more training, you can get it to identify cars around you, people, trees, lane lines, markings in the road, so on and so forth. It's all a matter of training it. And we use a technology called an RCNN. So an example of an RCNN is the YOLO V2. So YOLO is the you only look once algorithm, if you will. It's a neural network that you can download from online. It's already been trained on, I believe, 80 classes. I may be wrong, but it's trained on a large number of classes that you can identify a number of things, and you can look this up online. The next one that I want to talk about is semantic segmentation. This is another big application of deep learning, at least in the automated driving car space. You see what the network is doing is it's able to segment different regions in your image. So sort of the green area tells you, okay, this is a place that I can drive on as a car. The blue sort of tells you the different obstacles in its surrounding, and so on and so forth. So these are very powerful technologies, because all you need to do with this is you need to collect a lot of data. So as long as you mount sensors in your car and drive around, you're essentially collecting data. And then you have to do some processing to label it. But these networks are relatively, you spend a lot less time trying to make these things work. So it's deep learning is not just for images. You can also use them on signals. You've heard of signal classification. I'm not sure if a lot of you all have an Apple iWatch, but an Apple iWatch is able to essentially, it's a fitness tracker that's able to recognize if you're running versus walking versus climbing stairs, so on and so forth. It's all doing that based on it's able to identify these patterns in the signals of the different sensors on either on your watch or your phone. And it's able to tell you what you're doing, whether you're walking or climbing upstairs, walking downstairs, so on and so forth. But you can also do things like speech recognition. So speech recognition, as you can see, again, it's identifying these patterns, and that's the key with deep learning. You're always trying to identify patterns, and that's what these neural networks can do very, very well. So as I mentioned, deep learning uses neural networks, and the way a neural network works is it works in a very similar fashion to how the human brain works. Your human brain consists of a number of neurons that are connected to each other. That's essentially what a neural network is. You've got layers of neurons that are connected to each other, and essentially when you feed it an input, so say your input is some sort of an image, each of these pixel values go to each of these input neurons, so the neurons in the input layer, and then using some computations which you've probably heard of terms like weights and biases and activation functions. So essentially what a weight is, a weight means that it transfers, it's the weight, if you will, of how much of that information gets transferred from the neuron on one layer to the neuron on the next layer. Okay, so you'd multiply whatever your input signal is by that weight factor, and then each neuron downstream has what's called a bias. So you add that bias to the weight multiplied by the input factor, and the other term that you've probably heard about is an activation function. So an activation function essentially means that if that if the multiplication of the weight times the input plus the bias is greater than the activation, it'll fire off that neuron, right? So it'll activate the neuron, if you will. So essentially what's happening is as your data moves from the input to the output, you're essentially, the network is learning features, and it's able to match the features in the input to some output parameters. So say if you give it a picture of a cat, it's going to identify things like the tail, the ears, the eyes, etc., and essentially give you a probability score of what it thinks it is, right? And that's what comes out on the output side. But you also got things like hyperparameters that you can tune to improve the performance of this. I have a question in the chat that's saying image classification is machine learning or deep learning. This is actually it's a pretty nuanced question. You could do it by both ways. The difference is how much pre-work you have to do for it. So let's say you want to do image classification with a machine learning algorithm, something like a support vector machine or something like that. It is up to you as a programmer to extract features. So extract things like edges, color changes, region changes, foreground, background, etc. You have to do that manually. So you are extracting the features. And that's kind of the big difference between machine learning and deep learning. Whereas in deep learning, you can just feed it the image directly, and the network is able to extract the features on its own. So in machine, it's possible with both ways. It's just that with machine learning, you have to take that extra step of extracting the features for the network. So hopefully that answers your question. Okay. So again, applications, we've seen a whole variety of applications of deep learning. They're very versatile, but essentially what it comes down to is, most commonly deep learning is used for two types of activities. The first one is classification, where your output is a categorical. So what I mean by that is, and I'm just making up an example here, but say you have a data set which is a bunch of hospital information. Say, you've got a patient number, and then the columns have things like, okay, the patient has high blood pressure or low blood pressure, kidney problems, no kidney problems, so on and so forth. And you want to make a categorical connection of whether the person has a particular disease or not, right? So it's a binary problem, right? It's either you have the disease or you don't. Excuse me. So that is an example of a classification problem where you're putting it into buckets. So say you've got a bunch of images that you want to identify which one's a cat, which one's a dog. That's a classification problem. The other sort of application is regression. Now, this is when you want to have when you want to get numerical outputs or something that is continuous. So things like stock market prediction. You've got a your stock ticker chart is essentially, it's a time series chart. You've got some value of the stock price associated with a particular instance in time. Now, if you say you want to make a predictor that can predict the price of whatever stock 5 weeks from now, that's going to be a regression problem, because one is your output is numerical. It's going to give you a numerical value at the end, but it's also a continuous signal. It could be it is a continuous signal. So at a high level, these are a couple of applications of deep learning. Okay. So we're going to talk about a couple of different approaches for deep learning. The first approach is what you call, or what we call, training a neural network from scratch. And what I mean by training the neural network from scratch is you essentially assemble those layers of neurons together. This gives you the most flexibility, because you can, you obviously you have to know, you have to have some background knowledge on how to build these layers and so on, and what combination they come in, and so on and so forth. But you can essentially build a network that's either small enough for what you want to do, or larger than what research networks are. The sort of drawback with this is your network knows nothing. Your network does not know how to identify features. You've got to teach it everything. So you need a lot of data for it to learn the different features that you're trying to get it to detect. The second method is what's called transfer learning, and it's essentially using some pre-trained model. So there are a bunch of models out there. YOLO that we saw earlier. YOLO is a trained neural network. You've also got other neural networks like AlexNet, GooglyNet, various. There are a number of them that are available. So these networks are able to identify features, but they'll also map these features to particular classes, right? So, for example, let's take the AlexNet network, for example. It's able to identify that a cat has a tail, right? Now that having the tail or that feature of the tail is only in context of it being a cat. But what you can do is you can take that network and use its ability to identify edges, identify curves, identify regions where color changes happen, so on and so forth, but then map those features to an object of your interest. So you can say, oh, I have a network that's trained to identify cats, but it can identify the features as well. So let me use the initial portion of the layer of the networks, but only train the weights on the end. So the final output layer to map that to a new set of classes which I'm interested in, right? So this is it's a little easier to do. You don't need to have as much knowledge of how deep learning works. But you're able to apply transfer learning and take the work that someone else has done, and just sort of map these to features that you're interested in. I see a bunch of questions in the chat, so I'm just going to try and go through these real quick. Could you help differentiating between ReLU and GRU? I can send you a link for this. I feel like that's probably the best way to do it, just because it's a little bit of a specific question. But I'll definitely pop in a link when I get a chance into the chat for this. The next one is, can you clear my confusion between machine learning versus deep learning versus neural nets? I'm assuming that's what you mean. Okay, so this is you are right. These words are used pretty interchangeably. Essentially, machine learning and deep learning both work on the concepts of neural networks. Okay, so a neural network is essentially you can think of it as an algorithm, right? It's an algorithm where you pass in an input. The input fires off a series of neurons, and it's essentially it's firing off a series of neurons that's able to take whatever your input is and map its features to some output vector. So let me give you an example. If you want to train an image classification network to identify 6 different kinds of images, okay, so there could be cats, dogs, foxes, lions, and tigers, right? So 5 different kinds of animals. You feed in an input image to your neural network. Each of those pixels of the neural network, or each of the pixels of the image, correspond to one particular neuron in the input layer, and then these neurons, basically through a series of they could be convolutions. So convolution computations is essentially mapping the features of each of these pixels to one of those 5, and it's giving you a probability of one of those 5 classes. So like for example, you're never going to get, it's never going to tell you, oh, I'm 100% sure it's something. It's going to be a probability of something. So it could be like, I'm 85% sure it's a cat, but 1% sure that it's a dog, 5% sure that it's a tiger. So you're essentially giving you a probability of what it thinks it is based on how those input pixels have matched to the output features, right? And all this is happening sort of under the hood in the neural network. And then you essentially pick the one that it's most confident of. So whatever's the highest percentage, you say, okay, my network has predicted that's what it is. So machine learn. So the difference between machine learning and deep learning is based on the size of the neural network. So machine learning also uses neural networks, but they're sort of what they call shallow neural networks. So there's only a couple of layers of couple of middle layers of neurons. With deep learning, you sort of increase the number of middle layers of neurons that you have. So you've got, there could be 10. I've seen networks that have 30 layers, 50 layers, 60 layers. The more you go, that's what makes it deep learning. And if you, there's another question talking about AI or ML or DL. So AI is sort of the all-encompassing word that encompasses both machine learning and deep learning. As I said, AI is basically the ability to teach a machine how to mimic human behavior, right? Yeah. So that's what it is. There's a question that asks, does capture work in the same way? Kind of, yeah. That's essentially what's happening is, you give it an image, it's able to see if there are, it's going to ask you, oh, can you point the bridge out in this image, right? So they've trained a network to identify bridges, so it kind of knows what a bridge looks like, and it's able to, at the pixel level, identify what kind of an image it is. So what should I start with, considering that I'm a beginner? I think if you're a beginner, I'd say I don't think there's one particular thing that you should start with. I think definitely if you're a beginner, you should go and check out the MATLAB on-ramps, because we've got, and I'll come to it in a little bit, but we've got an on-ramp for both deep learning and machine learning that you can take a look at. It assumes that you know nothing. So it's a good place to get started. And I'll point you to a link. I believe one of the challenges at Local Hack Day is actually to do the on-ramp. So if you do that and submit the certificate, we'll give you some swag. All right, I'm going to stop with the questions, but I'm going to move forward with my presentation, but I'll come back to them in a little bit. Okay, so essentially, what is this deep learning workflow that we talk about? There are 4 big steps, right? The first step is you need data. You need a lot of data for deep learning, because that's the whole pretense of this argument, is you're using data to program, or you're using data to build algorithms, right? So you need to you need to access the data. You need to access it in some way. Typically you have large databases that could be stored in the cloud, using something like AWS or Azure or whatever cloud service you have. But they could also be data from sensors. Say you're working at a factory, and a big application of deep learning is actually if you're in a factory. Factories go through scheduled maintenance times, and what they're able to do using this thing called predictive maintenance. So it's a new field of artificial intelligence, where you essentially outfit your machines with a whole lot of sensors, and you're constantly collecting information from these sensors. And essentially what you see is you're able to identify these trends in the sensor data that helps you predict when a particular machine is going to fail, or when you need to replace a part, or things like that. So, that's one other application of deep learning, and that's why you need to access that data. The next step is labeling and pre-processing data. So we said, if you're building a classification algorithm that can identify different types of animals, you need to tell the network what the animal is, right? So you essentially what your input to the network is, you give it an image, but you also give it a classifier for it. So you say, okay, this image contains a cat. Okay. Now what's going to happen is that those pixels are going to move through the weights and biases, activate whatever neuron it has to activate in the network. And then it'll come up with a prediction at the end. So it'll say, okay, I'm like 60% sure it's a cat, 40% sure it's a dog. So now what you're going to do is what the network does is it uses something called back propagation, where it'll check what the output is against that classifier that you have submitted at the start. So the label that you have given at the start. If it's right, if your label is a cat and your network is more sure that it's a cat, fine, we can move ahead. But if not, it'll sort of move in the reverse direction and update those weights and biases to make sure that it's activating the right neuron. So, and you know, this is it's a pretty interesting concept. There are a lot of videos on YouTube about how these fire up and what are the actual computations that are happening in there. But the second big part is you need to label and pre-process this data, right? You need to sometimes it's possible that you don't have enough data, so you need to add things like filters to it, add geometric changes to the images, so on and so forth, just to augment your data set. So you've got you avoid overfitting. Okay. Oops. I'm sorry. And then the next one is you want to import these reference models. So, I spoke about AlexNet, I spoke about GooglyNet. There are a whole bunch of neural networks available on GitHub. If you can do a Google search for it, you'll find a bunch of them. But you want to be able to import these as well. So this is something that you can do in MATLAB pretty easily using this platform called ONNX, so Open Neural Network Exchange. This was, I believe, something developed by Facebook. And it essentially allows you to take neural networks that were built in one environment. So whether it's TensorFlow or Keras or MATLAB or whatever other environment you're building it in, but move them around between the different environments. So that's something you want to take a look at. The next one is sort of developing these predictive models. Right now, this is where you need the computational power. So you need to have things like GPU. GPUs, whether you want to accelerate your training, because imagine if you're working with, like, you typically work with thousands of images. It's not like the tens or hundreds, it's thousands of images. That's a significant toll on your memory, it's a significant toll on your processor. So you want to be able to accelerate that with the use of GPUs. You also want to do things like hyperparameter tuning to make sure that your network is not overfitting. I know there was a question about overfitting. So overfitting is essentially if you and this is why you need large data sets. If you give your network a data set that's too small, it's going to essentially look for exactly those features. So if you give it something that it's not seen before, it may not identify it, even if there's a cat in that image, because it has been exposed to a very small data set. It's not learned features, it's learned portions of those images, if that makes sense. And then you also want to visualize different aspects of your network, just so that you're able to see what the network's learning about as it goes through. And finally, you want to, obviously you're not building this neural network in isolation. You're building it as part of another system, whether it's in an app, whether it's on your self-driving car, or something that you want to put onto an enterprise system. And all that is all possible within MATLAB. So what I'm going to do next is I'm going to hop into MATLAB real quick, and I'm going to do a quick demonstration to show you how to build your first neural network. Okay, so let me just escape out of this. So what I have here is a simple time series forecasting example. So this is an example from the MATLAB documentation. Whenever you want to get started with MATLAB, my recommendation is just go to the doc. And if you go to the doc, you can, you go to all products and click on examples. And most functions in MATLAB have an example associated with it. So let's go to the deep learning toolbox, which is part of the license that we give you as part of our sponsorship with MLH. But essentially, you'll see a whole bunch of examples. This is one that's using AlexNet or GooglyNet to classify images. So it's getting in images from it's getting images from a webcam and it'll classify it. I see a comment in the chat that says, from what I've understood about machine learning, I think it's like a toddler. That is literally, you've basically hit the nail on the head with that. That's exactly what's happening. It's learning. You're trying to teach a mind that doesn't know anything something, right? So in an ideal case, it's funny. I like having these conversations with people that work in the field or work in this area, and they talk about, because there are always two sides of it. There's one side that's talking about, these robots are going to take over the world and so on and so forth. but then you see some of the problems that machine learning has. Like machine learning or deep learning sometimes, you can tell it's a cat, but it thinks it's like a banana or something like that. It's like these simple things that um, um, that are kind of funny. But ideally, ideally, in an ideal world, if the neural networks can live up to what they envision it to be, you're right. It's essentially like training a toddler, and then they start off knowing nothing, and then you sort of show them things, and that's how they're learning. That's essentially what's happening in a neural network. You show it something, it tells you what it is, and then you tell it if it's right or wrong, right? And if it's right, the network sort of rewards itself, right? It updates its weights and biases. If it's wrong, it makes corrections to come to the correct conclusion. So yeah, hashtag brain programmer. I like that. That's a good one. Okay, so I'm just coming back to these examples. This is something with deep learning, or this is an image based problem. What we're looking at is this one, the time series forecasting using deep learning. So I've got this example opened up here. It's a pretty simple example. I'm just going to run this section by section and walk you through it to see what's going on. But essentially what we're doing here at the start is we're loading this data set. Now, this is just a data set that ships with the product. So we're just labeling it, we're loading it and plotting it. And as you can see, it's a plot of monthly cases of chickenpox. So you see, there is some seasonal nature to it. The numbers go up and they come down, so on and so forth. Essentially, what our problem here is, we want to be able to predict that. Okay, we've got 500 months of information. Let's say we want to predict that. Okay, how many chickenpox cases am I going to have in month 510? Okay, so 10 months from now. So if any of you heard what I was talking about earlier, do you know what kind of a problem this is? Is this a regression or a classification? You can pop your answers into the chat. I'm going to give it 1 minute. If anyone gets it right, we get you. I don't know if we can get you a MATLAB hat or something like that. There we go. Regression is correct because it's a numerical value, right? So essentially what we're doing is we're exploring the data. We're just seeing what it looks like right now. Now, one thing that's very important. That's very important. We spoke about overfitting a little bit. The way to avoid overfitting is to always split up your data set into two parts. Okay, and the idea behind this is you use one portion of the data set, so the majority of the data set, to train the network, and then you use a portion of the data set that the network hasn't seen yet to test it. So you know that if your network is able to give you good performance on your testing set, which it has not seen while it was being trained, that means you know that it's not overfit to your training set, right? Because it's able to look at different data and still come up to the same conclusions, or conclusions up to your level of expectation. So what this section of code is doing is essentially just it's just splitting up these 500 data points into 450 data points for training and 50 data points for testing. So 90% of it is for train, and 10% is for and 10% of it is for is for testing. Okay. The next thing that you want to do is this is a pretty standard step in data science in general. You want to standardize your results, right? Or you want to standardize your sample set, just to prevent these huge outliers that you have, right? So essentially, what you mean by standardizing it is you essentially take whatever data point you have, subtract the mean of the entire data set, and then you divide it by the standard deviation. Okay, so it's just standardizing the data set around the zero, if you will. Okay, so this is it's. I'm just going to run this real quick to have this to execute this code. Now we've got to talk about predictors and responses. Now, what is a predictor? Predictor is a value that will help you predict what your response is going to be. Okay, so now if you think about this problem is essentially it's a time series, and you want to identify, say you have, we've got a time series of 500 elements. You want to identify the 501st first element of that series. So what is your predictor? Your predictor is essentially the element before you, the last element of the original series, right? So the 500th element is the predictor, and the 501st element is the response. Okay, so that's essentially what we're doing here. We're saying our training set is that standardized data vector that we made from the first element to the second last element, and then the response set is the second element to the last element. So there's a bias by one element, if that makes sense, because you're using the previous element to predict the next element. Okay. And then the next thing that you have to do is you actually have to build the LSTM architecture. So LSTM is what's called a long short-term memory network. It's a kind of neural network, very, very, very commonly used for signal type work. So if you're working with time series data, LSTM is one of the networks that are used for that. And what we have done at the MathWorks with the deep learning toolbox is essentially given you these functions that'll help build these layers. So here is a way of doing it programmatically. We've got a neural network that's got 4 layers. So it's got an input layer, an LSTM layer, fully connected layer, and then a regression layer. I'm not going to go into details with this because we can do like a whole talk on that, but I highly recommend you go and take a look at the documentation because it talks about what each of these layers do. So this is one way of doing it programmatically. Now, me personally, I'm not a computer programmer. I'm a mechanical engineer by but I studied mechanical engineering. I'm not a good programmer, so I like things that don't make me write code. And one way to do this is so MATLAB, we're striving towards building a low code environment, right? And one way for us to do this is we've introduced a lot of apps. So we've got something called the Deep Network Designer app, which you can use to construct your neural networks. So let me just pull this up real quick. It's going to take a second to load. Let me take some questions while we're waiting for it to load. Okay, someone was talking about the licenses. Yes, I know Rosendo just popped in a link to the licenses. Those licenses are valid for 3 months, but if you're taking part in another MLH event, you can always come back and get a new one once that one expires. So Devang asked a question: do we split the data into 3 sections? Yes, that is that is also definitely possible. People also do that. We just didn't have a whole lot of data here, but 80-10-10 is a good assumption. You also want to have some data for validation, and validation again. It's a more numerical way of validating your network. So you actually give it a parameter and say, okay, this is my miss rate is so much, or my my loss is, there are different parameters that you have. But yes, you could also see in an ideal case, you want to split it into 3 sections. We just didn't have enough data, so 2 worked. And again, I wasn't really looking to validate it, but if you're doing a safety critical application, you want to definitely have a validation set as well. Is machine learning an abstract neural network? I'm not sure what you mean by that. Machine learning is essentially what they call a shallow neural network. So you're still using a neural network, but it doesn't have as many layers as the deep neural networks are. Okay, so the deepness is classified by how many layers you have. So, for example, like the squeeze net, if I hover over this, you see that depth parameter, that's 18. Whereas GooglyNet is 22, ResNet is 50. So that's what sort of makes it deep, if you will. Okay. So again, so to build this network, you can either choose one of these architectures, or you can just choose a blank network. And essentially what you see are these, a bunch of these layers here. So like for example, if I have to build this same network out, I can grab the sequenced input layer, grab an LSTM layer, then a fully connected, and then a regression layer. I'm just going to search. And you can connect all these up together. Oops. And you can export this, and you essentially have that layer built out, right? So there are a couple of ways of doing it. You can either do it programmatically or with the app. I always prefer the app because I don't like writing code, but that's really up to you. It's up to what your preference is. Then you got to submit some training options. So again, you can take a look at the documentation for what these mean, but essentially you've got a solver. This initial learning rate and the max epochs. These are a couple of these parameters that you can tune to make sure your performance gets better over time. Okay. So we're setting up some training options, and now we're actually going to train the network. So let me just run this real quick. I don't know if I ran all of these sections. I did not. So you see what you have here is the network that's, or these are the layers of the network. If you click through this, it's currently got nothing because we haven't trained it yet. Okay. Now let's go ahead and train this network. Now I've got a GPU on my computer, but since this is text data, we don't really need something that powerful. But obviously we're working with images or videos and things like that. You want to have a computer that's a little more powerful, definitely with something with a GPU. But essentially what's coming up here, these are what you call your training loss plots. So RMSE is root mean square error and then iteration. So essentially what you want to see as this thing is training is the RMSE and the loss will start off kind of high, but then over time it should sort of converge and tend to go to as low as possible. So this is taking a little time because I'm sharing, but it's usually a lot quicker than this. But essentially what's happening is the network is being trained under the hood. I'm going to take some questions now while this thing converges. But question: can we build a neural network with the GUI and then later customize it with the code? Yes, that is definitely possible. And let me show you what I mean. So while this is training, if I go here and I click on export, I'm not only able to export this as a model, but I can also generate code from it. So essentially what will happen is that those few lines of code that you saw there, this will essentially spit out a function that has those lines of code in it. So you can go in and edit those parameters or edit the network programmatically. That's definitely possible. Yeah, so as we can see, it's it's sort of converging. The RMSE is now below 2. It's converging over time. It takes we've set it to we set it to do 250 iterations, so it'll either converge before that or finish at 250. But yeah, I'm just looking through to see if there are any more questions. So there's a question saying sometimes we increase the epochs to increase the data passes into the neural network. It decreases the accuracy instead of increasing it. Yeah, these are very specific situations. This is definitely something that you learn. There is a fair amount of trial and error involved with this. So like I know I have people on my team here that when we design networks, we are spending a lot of time, just like playing around with those parameters, training it again, seeing what happens. So I mean, unless we look at the exact case, it's kind of hard for me to make a comment on that. But yeah, I mean, there's a lot. A neural network is a black box. Is very much a black box in a lot of ways. So sometimes you don't know what's really happening under there. I have this very interesting story. I was talking to a professor, and they were building a self-driving car, and they were driving. They had this car, it was working well. They had built a network to train it on identifying lane lines. The lane lines in your car or on the road, and they thought it was working fine until the car went over a bridge. And the car goes over the bridge, and then it like completely loses its mind. Doesn't know where it is, doesn't know what's happening. And it was only after a few a few months, they realized that their network was, although they thought that they had trained it to identify the lane lines, it was actually identifying the edge of the grass along the highway. Which is, as you can think of it, it kind of looks similar. They're both lines sort of separated by illumination regions, if you will. So when it went over the bridge, it wasn't seeing the grass anymore. So it sort of lost its mind. So it's one of those cases where there is a little bit of a black box nature to this, to deep learning, and sometimes you have to try and fail before you learn what's happening. Okay, so this is the training has progressed. We can see that our network has been built here. Now we want to forecast these time steps. So again, what we're doing is we're standardizing the test set. We only standardized the training set earlier, but we're also going to standardize that same, subtract by the mean and then divide by the standard deviation. And then now that we have our set, let's predict it. Now what we want to do is we want to predict and we want to update the state of the. So I'm going to run this real quick. So it's essentially what we're saying is, okay, now that we've got 450 elements, when we find the 451st element, we want to update it with the predictions. Or when we're looking to find the 452nd element, we want to use the predicted 451st value to compute the next one, right? Because that's what's happening. We're using the previous element to predict the next one. And you can see what's happening is, we've got everything that's in blue was what we got from the data set. Everything that's after that in red is what our network has predicted. Okay, so if we sort of zoom into that to that little bit of data, here what we're doing is we're comparing it with what our testing set had, right? So you can see it's kind of off a little bit. It's meeting at some points and it's sort of following the same trend, but it's not. It could perhaps be a little more accurate. Now, what you can also do is you can you can reset the network state, and this will help you improve your performance a little bit. So what we're going to do is, instead of using our predicted values, we're going to use the observed values. So say once we get to 452, we're going to replace that with the observed value, and then predict the next one, just so that we're able to get a little better performance. So let's run this and see what happens. So the RMSE error that we got earlier, so it's 144 in this case. What was it earlier? It was, I believe, 207. 207. So we saw that we saw that we're able to improve the performance a little bit by updating the network state with these observed values. Again, this example is in the documentation. I showed you how to get to it, so you can go and take a look at this on your own time. see what's happened. But as you saw, it's without knowing a whole lot of what's going on, I was able to open up a documentation link in it. Now, think of all the applications with this. You could do stock prediction with this. You could do predicting the number of, I don't know, since COVID's the big thing now, predicting the number of COVID cases around, predicting the number of, there are so many different kinds of applications that you can get just from this example. Okay. So I see we've got about 10 minutes left. I'm going to go back into the presentation real quick and do a quick wrap up, just in the interest of time. Okay. So let's talk about some hackathon user stories. One of the the MathWorks, we started supporting hackathons in late 2020. It's something that's new for us. We've been doing student competitions for a long time, but hackathons are relatively newer. One of the first ones that we sponsored was New Hacks 2020, and it was at the University of Toronto. And this was a really cool application because this was right around the time when everyone was doing virtual learning. We were all still on Zoom calls. I know we're still on Zoom calls now, but that was everything that we did at that time. So what this group of students did from the University of Toronto was essentially in a day they figured out a way to tell the professor who's teaching the Zoom call if the students in their class are paying attention or not. So what they've done is they've trained a neural network that can do it. Essentially what it does is it says if the person's looking straight into the camera, they're focused. And this is a video. Let me just play this. But if they're looking in the camera, they're focused. They're looking away, they're distracted. And they connected this neural network that they trained in MATLAB pretty much in a day to a Unity front end. And they were able to give the professor a little bit of an app to judge how his or her students are paying attention in the class, and then alternately make changes to their lectures so that it's not as boring. Okay, so this was cool. We've got a blog post here that they've written with us. I can send you a link to this in the chat if you want to take a look at it. But I think Rosendo can send it to you. I'm just going to send it to him real quick. But this was one cool application. The next nice user story that I have, again, this was built in one day, again using the deep learning toolbox. And this group of students from Texas A&M, they essentially build a movie recommendation app. So this was funny. The night before the Tamu Datathon hackathon, they were all hanging out together trying to watch a movie, and they couldn't decide which movie they wanted to watch. So they were like, oh, I like this movie. Someone else likes that movie. So like, oh, let's just make an app for it. So what the app does is it takes in a poster, and then it uses what's called an autoencoder. So an autoencoder is a different kind of neural network. It's kind of like an like you have an LSTM, you've got autoencoders, which are different kinds of neural networks. And they essentially based on what the poster you give them, it'll make another recommendation for you based on what it's seeing similar things. So for example, it looks at the Superman poster, sees someone flying with a cape. It's able to identify similar features or action shots, if you will, in the Avengers poster. So it recommended that. Similarly with the horror movie down here. This group also wrote a blog with us. I can ping a link to that again in the chat. Rosendo can help you out. But yeah, so these are a couple of examples. Again, built overnight. It was built for a hackathon. It was not something that they had started working on before. But because MATLAB is such a low code environment, they didn't really have to worry about is my syntax right or not. There are examples, there are apps that you can take and get started. So it helps you get your work done quickly rather than sitting and worrying about how to write the code. Here are some resources for you. We've got an awesome MATLAB hackathons repository on GitHub. If you go, so what you can do is you can go ahead and clone this repository, and then you have access to it. It's got a bunch of different resources. So it talks about how you can use MATLAB for deep learning, how you can use MATLAB for working with hardware, whether you've got like an Arduino or Raspberry Pi, you can program that with MATLAB. There are a bunch of links up there that you can take a look at. as well as the you'll find information on how to get your license for MLH. So that's something to keep in mind. I recommend that you go take a look at that and clone the repository. We just launched this a couple of days ago, so it's fresh off the presses. The next thing I want to talk to you about is the MATLAB Central community. There are over 2 million MATLAB users around the world. Okay, whatever you are trying to do with MATLAB has been done before by someone else. They've definitely done it before, and they've probably shared the code for it. So this is a good place to find code. Whenever I start writing new code, the first thing I do is I go to MATLAB Central and see if someone's done it before. But you also got things like MATLAB answers. If you have a particular question, you can post on there. Someone will answer it for you. There are a lot of math workers that are sitting on there to answer these questions, and so on and so. So file exchange is where you can find code. Blogs are what you can take a look at. ThinkSpeak is our IoT, so Internet of Things platform. Again, it should be free with your license, so you can go and explore what works there as well. Okay. These are the complementary on-ramps. These assume you know absolutely nothing. So if you're a little bit of, if you've got some programming experience, you can breeze through these pretty quickly. But these are all free. You can go take a look at it. You don't need a license to learn this. You don't need to download the product even. It's all in the browser. So I highly recommend you go take a look at it. We've got one for MATLAB, machine learning, deep learning, optimization. There's a whole bunch. Simulink as well if you want to learn that. But these are complementary and available on our website. You can just Google search MATLAB on-ramp and it'll take you there. And the next thing is we've got career opportunities. We've got offices all over the world. I believe in 16 or 17 countries. So we're pretty global. We've got this program called the Engineering Development Group. This program is currently in India, in the UK, and in the US. So if you want to work for us, or you want to do an internship with us, or you want to be a student ambassador on your campus, please reach out to mathworks.com/studentjobs. There's a whole web page for you over there. Go take a look and see what suits your fancy and apply for it. We're always looking for. We've hired a few students from various hackathons, and we want to continue doing that because we really like your passion. The fact that you want to go out of your way and learn and try new things, that's very attractive to us. So if you're looking for a job, please go check this out. This should be something for you. All right, so that's my presentation for today. Let's take a look at some of these slides or some of these questions real quick. Let me just pull up this. Okay, I'm going to try and go through some questions. If you have any more questions, please feel free to ask. I'll try to answer them. Okay. I'm going to try and scroll up and see when was the last one that I answered.
Hey, Connell. Yeah, we've got time for maybe one or two more questions.
Yeah. Yep. Okay. Yeah, I see. We've got 2 minutes left. So I'm just trying to see. It's a lot of chatter. Can't really find any questions.
You want me to drop something on the screen for you?
No, I can see one. Can we visualize the parameters of the individual? Yes, you can. There are ways to probe into the network. I believe we've got an example on this. So I recommend you go and take a look at the documentation, but it's definitely possible. How many nodes should each layer of the neural? So this is something that I can't really answer. It really depends on your application. This is when you want to have some knowledge of neural networks. But it's good to try and see and sort of work it out from there. You definitely need a little bit of domain knowledge for that. Is there any doc for the supported deep learning libraries? Yes, take a look at the documentation. You'll find everything in there. Every function has a documentation page. Okay, I think that's it. I don't think I see any more questions. Yeah, I think we're good, Rosendo. I don't see anymore.
Sure thing. Once again, thank you so much, Connell. It was wonderful seeing you work, and honestly, it looks like everyone else had a great time. Just remember, y'all, we have Ryan and Mary coming up soon, so you'll need to refresh your page in order to see their stream come up. But for now, we're going to be checking off. Really appreciate y'all joining us. Have a great day, y'all. Remember, check us out on Discord. If you didn't get your questions answered, you could always drop them in the Discord channel for in the MathWorks channel. All right, y'all. Have a good one.
Thanks, everyone.